In the last video, we learned how to write electron configurations for smaller elements. And right now I want to add on to that a little bit and teach you how to write noble gas electron configurations, which saves you a lot of time and effort when you're looking at larger elements. So just to recap, if you look at the periodic table and you take helium and move it from the far right side to the left side, this entire region, the first two groups, would be considered the S block, which means they're filling out, their outer electrons are filling up the S subshell. In the middle region, we have elements that are filling out their D subshell, which is actually in an inner level, and we'll talk about that in a little bit. Far to the right, we have the P block, or elements filling up the P subshell. And then down here, we have the fourth energy levels and fifth energy levels, F subshells, which come in way later. All right, so if we read this periodic table like a book, we read from left to right and then top to bottom. So the first energy level contains only an S subshell. So it would be 1s2 when we get to helium. Now the reason helium finds itself far to the right on the periodic table, even though electronically speaking it's filling out its S subshell, is that its outer energy level is complete, so it acts like a noble gas. Once we finish that first row, we have the 2s, then the 2p. Then we have the 3s and the 3p. And before we get to the third energy level's D subshell, as we showed in the last video, the fourth energy level's S subshell is actually lower in potential energy, so it fills up first. So we go the 4s and then the 3d. So these electrons filling up are not technically considered valence electrons, or electrons in the highest energy level. But once that D subshell fills up, 4p6, and then we start a new row. 5s2, 4d10, 5p6. And then what's going to happen is, in the sixth energy level, we're actually going to start filling out the fourth energy level's F subshell as well. So it goes 6s2, and then you might notice that the periodic table goes from 57 to 72 right here, and everything in between is listed below. These are called the lanthanide and actinide contraction series when they come in. So it goes 6s2, 4f14, and then it goes 5d10. So just remember, D subshells are always buried by one energy level, F subshells are always buried by two energy levels. Then we're going to hop back over to 6p6, 7s2, and we're going to hop back down to 5f14, and then 6d10. And you can see that there's a lot of stuff in the elements in the bottom few rows of the periodic table, and that becomes kind of cumbersome to write. So let's do a quick example, and I'm going to show you how I can write it in a shorter fashion. So if we're looking for chlorine, which is number 17 on the periodic table, over here, the member of the halogen group. If we write its electron configuration, it's 1s2, 2s2, 2p6, 3s2, and then 3p5. And that's how you would write it. Now, you can actually shorten this quite a bit because atoms are very superficial and they only really care what's on the outside. So everything that's up to the noble gas before it is considered an inner shell electron. And in reality, it's never going to react with its inner shell electrons, only what's on the outside. So we could write this in shorthand by summarizing everything up through 2p6 as neon. So you write the noble gas that comes before the element, and then whatever's left in the outer shell, which would be the 3s2 and 3p5. If we were to pick another element, such as, say, let's look at tin, which is right here on the periodic table. You could write quite a bit. You could write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, and then 5p2. Or you could simply just write, for tin, you could write the noble gas that comes before it, which in this case would be krypton, and then write whatever else is left in that shell. So after krypton would come 5s2. And then you would write 4d10. And then after the 4d10 fills up, you have 2 electrons in your 5p subshell, and that is how you would write the noble gas configuration, which saves you quite a bit of time.